welcome to the Newton Institute, and welcome to our Spitalfields Day of talks on gauge theory, string theory, and unification. As you're going to hear, next year, the biggest and most powerful particle accelerator to date is going to start operations. And this accelerator has the potential to make more discoveries than have actually been made during my career as a professional physicist. So I think for many of us in the room, we're going to sort of see this as an epoch-making opportunity. We're going to see our careers as before the LHC and after the LHC. To kind of mark this, given at the moment the current program running at the Newton Institute is being attended to by particle theorists from around the world, we thought it was an ideal opportunity to present to you some of the current thinking as to what the LHC might actually find. So you'll be hearing about things like the Higgs boson and about mysterious concepts such as supersymmetry. Before we start, however, Tom Kerner from the London Mathematical Society, who are very kindly supporting this event, would like to say a few words.
Okay, well, it's really addressed to the back because the front knows all of it. Why is the LMS called the LMS? Because calling it the Society for British Mathematics, excepting Scotland, which is represented by the Edinburgh Mathematical Society, is a bit long. It does good by stealth, but it feels it shouldn't be too stealthy, which is why I'm here. One of the things it's just done is that it's rescued the new Journal of Topology from the jaws of the capitalist blood-sucking publishers. And why I'm anxious that the people in the back should hear is that EPSA, in its endless search for cures for which there is no known disease, has decided that that graduate students should be able to join professional bodies free. So you can go to the desk outside and join the LMS for free. And when it becomes non-free, you of course do not need to renew your membership. Now, the LMS is 150 years old, but in England, everything is judged by its age, so 150 years is not quite enough, so you've got to find some predecessor, and historical research has revealed the Spitalfields Mathematical Society, which, if you stretch an enormous amount, brings us back about 200 years, but you have to stretch an enormous amount. Now, the LMS feels that long-term programs like this should have a day in which the specialists talk about what they're doing to the non-specialists, and as part of the program of making the LMS seem older than it is, we call these Spitalfield days. The only other point I have to make is that in the original Spitalfields Society, it was discovered that if you stopped offering food and drink, fewer people came. So the LMS insists that there should be a little bit of wine and tea for everybody. So that's all I have to say. On with the proper show.
Thank you, Tom. I believe the hospitality today will extend to cake at tea time as well. Just before we start, one piece of housekeeping. Some of you have been offered support for your travel. For those of you who haven't yet lodged a claim, please do that during the interval at reception. Go to reception and ask for, tell them you want to make a travel claim. Okay, without further ado, can I ask Nick Evans from Southampton University to tell us about the LHC?
Thank you, Simon. Okay, so what I'd like to do is to try and get you excited about this thing that's happening right now in Switzerland. And I want to try and tell you a little bit about the experiment. I'm a theorist, so you'll have to excuse me, but we really need to talk about this thing. It's a very exciting bit of technology and engineering that's going on. at the moment. It ties into a massive mathematical and intellectual physical endeavour that's been going on for 500 years. It's a very impressive structure intellectually as well. You know, people out there think that the pyramids are impressive. This thing blows its socks off, and people should be talking about it more. Okay, so as I say, what I'm going to do first of all is just give you an oversight of what this thing is and give you some of the astonishing numbers that go with this machine. So it's in Geneva, and here's a picture of Geneva. This is Lake Geneva here. This is the airport, and this white ring is our experiment, the LHC. Now it's actually 100 meters underground roughly, 50 to 175 meters I think in various places. It's 27 kilometers round this ring. And of course what this is going to do is tell us about the structure of matter, and I'll sort of introduce you to what it is that we're hoping to learn. And it's going to start doing science next year, so we're all pretty excited by that. Okay, so what's it going to do? It's going to collide the nuclei of atoms at 10 times higher energy than we've ever collided them before. We're going to smash this stuff together and see what comes out, and from that deduce what is going on in the cores of atoms. So the hard number is that there's going to be 14 tera-electron volts of energy available in the center of mass. So how do you get things going that fast? All of these things are going to be basically traveling at the speed of light. Well, here down in the tunnel, you have a vacuum pipe, which the beams are going to be in, and then you have 1,232 magnets, each weighing 35 tons, that are there to put these particles into little bunches and then control where it is that they go in the machine so that you can eventually bring them together at these very high energies. So another amazing figure is to have these superconducting dipoles working, you need 36,000 tons of coolant below 2 Kelvin, which is the most coolant in any one place on the planet at the moment. So the real frontier physics, I think, is going to come out of proton-proton collisions. So a proton is the nucleus of a hydrogen atom, and we're going to smash these things together, let's say at 14 TeV, and see what happens. So we're going to do it once or twice? No. Each bunch of particles going round this ring has about 100 billion protons in. Every time we cross these things, there are actually going to be about 20 of those things will collide and actually produce some sort of interaction. And in order to see enough things going on, we're going to actually cross these things every 25 nanoseconds. So in total, there are going to be 600 million collisions in this machine every second, which is pretty shocking. And this is an example of a collision simulated as to what it will look like. And well, I'll talk to you more about what all this means shortly. But you can see there's lots of data there. And in fact, if one wanted to collect all of the data from all of these collisions, you'd be collecting about 10 petabytes of data a year. I read somewhere that that's about a 20-kilometer high stack of CDs. To actually collect all that data requires more CDs than mankind knows how to produce, more hard drives than mankind knows how to produce. So actually you have to be very clever in 25 nanoseconds and decide whether something you're seeing is interesting. It's called a trigger system. And we have technology, chips basically, that look events and chuck out most of the events that aren't interesting on this sort of timescale. Okay, then how do we actually see what's going on in the events? Well, we have detectors, and there are 4 of these at LHC. Atlas and CMS are going to be really interested in those proton-proton collisions. There's going to be a special experiment that's interested in B quarks, which, excuse me, I'll leave to one side. And then there's another experiment called Alice, which I'll come back to later. But what do these things all basically look like? Well, they basically look like a house, right? These are enormous machines or enormous experiments. So coming down the center here is that evacuated beam pipe in which you're going to make the protons collide. And then what do you want to do after the collision? Well, you want to see what comes out and where it goes. So right in the center there is, something that is a sensible size that you could almost sort of get your arms around, called a tracking chamber. That has lots of detectors, very carefully spaced, very closely spaced, so that you can see the particles as they go through and get a very good measure of the tracks. So you can sort of think of it as just a grid of wires, if you like, and as the particle goes past, it ionizes that wire and you get a readout of where the particle is. Okay, very crudely, then what's outside that is a whole bunch of lead. Okay, so all of this stuff here is lead, and in amongst all of that lead and so forth are detectors. And what you're basically doing then is just you're trying to slow these things down. They come out with enormous energies, you want to stop them and read out how much energy they've got. So, for example, something like an electron or a photon gets stopped in a few meters of this stuff. Something which is made out of nuclear matter goes several meters more, and then there are a few strange objects such as things called muons, which you really have to try very hard to stop. And so there are sort of layers of what we call calorimeters, and depending on how far things penetrate through, you can tell what particles you're seeing. So we track the particles, we measure their energies, and also in that central area you can have a magnetic field. A charged particle moving in a magnetic field will bend, and from that curvature you can actually measure the momentum of these particles. So that's what this sort of house-sized lump of lead is doing for us, is telling us what's coming out of these collisions. And this is a picture of one of these detectors being built, and hopefully you can see, you know, these are ladders and so on. These are enormous bits of machinery. Okay, if you want to build a 27-kilometer ring full of more coolant than anyone else in the world has, it's going to cost you some money, and I think we have to defend our use of £2.6 billion. And that sounds like an awfully large amount of money. But I want to just put it into perspective for you. How much is £1 billion? Here are some examples. Sky Television paid about £1 billion in order to show football to the world for 3 years. That's not that much, is it? Around the world, people have spent £1 billion in various ways in order to watch Leonardo DiCaprio muck about on a boat. So £1 billion is not that much money. Now we get into sort of the bigger league. The British people spent £19 billion in Tesco's last year. The NHS is about £20 billion a year, and about £35 billion is spent in this country on beating people up. So this isn't a small amount of money. It's comparable with this, except that this is going to be spent over about 10 years. This is actually being spent by 20 member states of CERN and a number, probably about 10 other big players, including the US. So if you were to put these numbers down for all of those countries, this is starting to be fractions of a percent of these sorts of numbers. And I think if you think of it in that terms, it would be pretty shocking if, as a civilization that has built itself on science, we weren't spending roughly the amount we spend on watching a good film on doing fundamental science. If that doesn't convince you, then actually you guys already owe us, because during the last experiment called LEP, the guys at CERN were trying to work out how to exchange information quickly, and somebody called Tim Berners-Lee actually invented some protocols that let computers talk to each other, which has now become the World Wide Web, and he just gave it away. It's not really particle physics, so it's not interesting, right? I couldn't find figures for the total revenue spent on the internet last year that we should get our chunk of, but for example, £7 billion was spent on the Amazon site last year. So I think, you deserve to give us this much for that reason in life. Okay, so that's the machine. What I now want to do is to talk about what it's going to do, what is the intellectual edifice that we're trying to test and improve with this machine. So what's the story of our understanding of matter so far? Well, tables, computers, all of these things we've discovered are made out of molecules that are made out of atoms. And the difference between different atoms is that they have a nucleus and then they have a different number of electrons orbiting around them, and those electrons are kept tied to that nucleus by the electromagnetic forces. And of course, basically everything in everyday life, the reason you don't fall through the floor, chemistry, all of industry and so on, is just to do with moving these electrons around in their orbits between different atoms. That's what chemistry is. Okay, what else is going on in here? Well, inside the nucleus of that atom, we've discovered that there are positively charged protons. They're the things that keep the electrons bound in. and some neutral things called neutrons. In fact, though, you can go and you can bust up those protons and neutrons, and you find that they're made out of things that we rather esoterically call quarks. And I'll talk more about all of that shortly. So it's actually a very, very pretty picture. Everything in this room is made up out of electrons, so-called up quarks and down quarks. And that's all you need to make essentially all of the world that we see. There's one other guy that's important, which is the electron neutrino. This guy doesn't really speak to anything in this room except in nuclear decay. So, for example, in beta decay was where it was originally discovered that in order to conserve energy and momentum, you needed this extra particle that has no other interaction properties. But these days we know they exist, and if you take a very large tank of water and you point it at the sun, you see the occasional flashes as these neutrinos come through, and you can take this nice photograph of the sun in its neutrino light. So we need these things around in order to actually make the elements and so on, but otherwise that's basically what the world is made of. And you know, if it was just a matter of breaking things up and seeing what they're made of, it wouldn't really be so exciting. The thing that is interesting is the way that the theories of nature and your expectations of the way things behave changes when you go down to these very small distances or these very high energy scales. I'm going to take you through just quickly the four main theoretical advances that have sort of built our construct, which we call the standard model of particle physics. Okay, the first one is special relativity, thanks to Einstein. And this is this bizarre observation in the universe that the speed of light is the same for any observer. So in particular, that immediately means that nothing can travel faster than the speed of light. If you could travel at the speed of light, you'd be going along with the light and the light would look stationary. So Einstein had to change our laws of dynamics so that if you wanted to get something to go at a speed v equal to the speed of light c, you would have to put in an infinite amount of energy in order to boost to those high speeds. So the famous E equals mc squared equation with the gamma factor in. And of course then what you notice from that sort of falls out for you is that if v equals 0, E equals mc squared, mass is a form of energy locked up in a particle. And part of what I'm going to talk to you about today is what that energy of interaction is. Okay, and of course we use this all the time in particle physics. If you want to make new particles, you just collide things together, put some energy into a small space, and let E equals mc squared create it for you. The other big theory is quantum mechanics, or the so-called wave-particle duality. And again, this is just an observation that nature has taught us how to do this. If you look at some wave, like an electromagnetic wave, and you try and drain the energy out of it, you find it doesn't come as a continuous stream. You get it coming out in lumps or quanta, whose energy are given by the frequency of that light or wave and Planck's constant h. Okay, so for example, for an electromagnetic wave, these lumps of energy that you can get out of the wave you can think of, if you like, as particles, and we call them the photon. So what we've basically been taught by nature is that a particle of definite energy is associated with definite frequency, and likewise something with definite momentum is associated with a wavelength lambda. And so a nice sine wave like this is something that has a distinct energy and momenta, but as you can see, it's completely spread out in space. On the other hand, if I try and construct something where the particle is localized at a single point in space, and I try and construct this by Fourier analysis out of a whole bunch of sine and cosine waves, what I find is that I have to sum an infinite set of these to get something this spiky. In other words, I know where the particle is, but now I've got all possible momenta contributing to that setup. So then you can have a compromise, you can have a little wave packet, but then the compromise is given by Heisenberg's uncertainty principle that delta x times delta p can't be smaller than some number h bar. In other words, there's always some uncertainty in position and momentum, or equally in energy and time. And in a sense, that's where the weirdness of quantum mechanics comes from. if you go down to very short distances, very short time scales, suddenly you can cheat the classical laws of motion by just grabbing some energy and momentum from nowhere and deviating from the classical path. So both of these theories are necessarily part of everything we do in particle physics. And it actually was quite remarkable what happened when people brought them together. And since we're in Cambridge, I'd better put up a picture of Dirac, who was one of the sort of formative people in thinking about this. So a sketch of where some of the miracles happen is just this. Well, we know that an electron can absorb a photon. That's what happens when things heat up and emit light and so on. But in relativity, we're supposed to treat space and time on an equal footing, so there's no reason why I can't rotate this diagram so that I have this rather strange setup where the electron comes in and then bounces backwards in time, emitting a photon forwards in time. And you might have thought that these were just crazy solutions, but actually, if you think about it, this charge going backwards in time is just like a hole moving, basically. This is something that looks in every sense like an electron, but with the opposite charges. So that was a remarkable prediction that every particle should come with a twin, an antiparticle. And of course, experimentally, we've now discovered these things, first of all in cosmic rays, but now they're part of our general collider program that we can create from a photon running this backwards. A photon could come in and create an electron and a positron. Okay, so that sort of doubles our spectrum. But there's something really remarkable about these theories that actually gives us the theories of force for free. And we call these gauge theories. So my wordy sketch, and then I'll quickly take you through the maths for those guys who are tougher in the audience, is the following. So we've discovered that there are particles and antiparticles, and the only thing that's different is that they have opposite charges. So which do you call particles and which do you call antiparticles? Because it doesn't matter. But the problem is that in the universe there are causally disconnected bits of space, right? Because light can only travel at the speed of light, there are areas that can't talk to each other. And they have to make a decision as to which convention they're going to use. But then it's confusing when those particles come back together as to which which convention are you then going to use? How do you know which convention the other bit of space was using? And nature's invented a force, basically, to allow those two particles to talk to each other and say, which convention are you using? And that force is electromagnetism. So more formally, if you take a wave equation describing a charged particle and its antiparticle, there's a phase dependence. Well, so the point is that you can make a transformation where the phase of that wave function, i.e. mixing the real and imaginary parts, can be spatially dependent. And if you want to make it that this phase really can be different in two different disconnected bits of space, and you want the physics to remain invariant when you do that, you can only do it if you introduce some new field with a mu index. So this is what we call a gauge field. It's a vector. And you're forced to introduce it in this way into, say, the Dirac equation, and for it to have this property here, which maybe you recognize as being the fundamental gauge invariance of electromagnetism. So just by these sort of waffly words and demanding suddenly this mathematics, you've actually invented the whole of electromagnetism. And that's how now we get all of the forces in particle physics. We have some, as we call it, symmetry that we want to impose that is local. We can do this differently at different points in space, and it gives us for free the theories of force. Okay, so those are sort of the four key elements of our theories, and I want to now try and bring them together and show you some of their remarkable consequences. And in particular, I want to concentrate on the issue of where do particles' masses come from. Why is it that you're sat in this room and not streaming around the universe at the speed of light? Okay, well, what I basically have to do is to put two of my equations together. The uncertainty principle says, well, for short periods of time, about the time it takes for light to cross an atom, I can borrow energy, as long as I then sort of pay it back later on. But then we also know that we can use that energy to create particles because E equals mc squared. So the traditional view of empty space is immediately gone because in a quantum theory you can pair create an electron and a positron out of nothing and it'll be there for a short while and then it'll disappear again. So the quantum vacuum is a seething mass of these particles. Well, but if they're only there for these fractions of a second, how do you know? Why do you care? And the answer is that you have to take these into account if you're going to get the answer to anything right in particle physics. For example, you might want to look at two electrons interacting by the electromagnetic field. If it's not a very big interaction, they might just exchange the smallest amount of energy they could, exchange a photon, a quanta, between the electrons. Now, you can calculate this, and you'll get the answer right to about 1%. But the moment you start trying to do a more precise measurement, you'll find you're wrong. And the reason that you're wrong is that sometimes when this is going on, in the vacuum, an electron and a positron will be created by the uncertainty principle for a little time. The photon will then get impeded by those pair, might get absorbed and then re-emitted, and that will change the answer. Now, this interaction is quite weak, so it's not a big effect, it is just 1%. But if you don't include these sorts of diagrams, you get the wrong answer. So it really is true that the vacuum is full of this stuff. Actually, our theories of this, so quantum electrodynamics, is astonishingly well tested. If you look at the magnetic interaction between an electron and a magnetic field, you can measure something called G-2. This is the magnetic dipole of the electron, sorry, the magnetic moment of the electron. And you get some number which you can find the corrections to. So the number, if you ignore these corrections, is 2, which is why you measure G-2. But anyway, this thing has now been measured to 13 significant figures, and it agrees with what our theories say. Which is astonishing, and in fact, in terms of doing these sorts of calculations, it's what we call for-loop diagrams. In other words, you actually have to have 4 of these sort of pair creations going on in there, and some interaction that includes all of them in order to get the right answer. This is probably the most stunning test of a theory of physics that we have, and it's really very impressive. Another way in which you can think of this is, well, here's a sort of a toy picture. Here's my bare electron, my basic electron, and then around it there are all of these pair-created electrons and positrons, which of course get polarized by this thing in the middle. And so this sort of smears the charge out through space. So one way in which you can think about the effect of these loops is that the effective strength of the interaction between two electrons depends on their separation. In other words, how far into this muck you bring the other electron. And so we have what we call a running coupling, that the electric charge of an electron actually depends on the separation of the two things that are interacting. Now, if you just talk about electromagnetism, it's a pretty small effect. Day to day, doesn't have a huge impact on your life. When we come, though, to talk about the strong nuclear force, we're going to see that those effects are much more important. So let's just sort of backtrack. So here we had our atoms with the nucleus made of protons and neutrons, and then those were made up out of quarks, and in fact 3 quarks. So for example, a proton is 2 up quarks and a down quark. So, you know, you can try and smash these things apart and look at the properties of these quarks, which people have done in accelerators before, and we find something interesting. These things are charged. Of course, there must be some force that's holding them together. That's what the strong nuclear force is. But it turns out that this force, rather than being like electromagnetism with a sort of charge, plus charge and negative charge, there are actually 3 different sorts of charge, which, well, we call them red, green, and blue. But really, that's not the right thing to do, because these particles are indistinguishable. So nature, again, has the problem of, in one bit of space, it might call this type red, this green, this blue, and over here it might have made a different set of choices. Again, you need something so that when you bring those things from the different patches together, they can talk to each other and decide, you know, which convention was I using. And that's where the strong nuclear force comes from. So it is a gauge theory as well, associated with an SU3 group. The 3 is just, well, the group SU3 is just about the rotations of changing your definitions of what these different colours mean. Okay, it turns out that there are 8 equivalents of the photon in this theory, and the reason for that is that if you've got a red quark and a green quark, the way in which they work out their phase conventions is that they interchange their charges, so they become green and red. I got that the right way around. So then the gluon going between them, as it's called, this sort of photon-like object, carries red anti-green charge, for example. And so because you can have red anti-blue and so on, there are actually 8 of these guys in the theory. Now the fact that these gluons carry charge, right, a photon doesn't have any electric charge, the fact that a gluon carries charge greatly changes the way in which the vacuum polarizes around a charge. So just as I was showing you on the previous slide. And the difference is actually due to these gentlemen here, one of whom we will hear from later, is something called asymptotic freedom. When you look at how the interaction between 2 quarks changes as you change the separation of 2 quarks, you find that when they're on top of each other, they don't interact, whilst when they're very far away, they start to interact more and want to come back together. So it's asymptotically free, means that when you put them on top of each other, the interaction switches off. So this is very peculiar, right? I mean, if you take an electric charge and another electric charge and you take one of them off to the Andromeda galaxy, you can just forget about it. If you take a quark, an unpaired quark, off to the Andromeda galaxy, you get a massive force restoring those 2 quarks back together. One result of that is what we call confinement. It means that you can never actually take a proton and bash it so hard that you knock a quark out, because the further it goes away, the more it just wants to come back. So some people find that confusing, but I think once you've seen the theory, it's just clear that that's what happens in this theory. So you can never liberate a quark from one of these hadrons, as they're called. I want to concentrate on the effects for the quantum vacuum, though. Because, of course, you know, every so often, using the uncertainty principle, you can create a quark and an antiquark. But now they interact very strongly, and if they go far apart, they interact very, very strongly. There's a huge binding energy. And it turns out that that binding energy is actually greater than the energy you originally had to borrow, if you like, to create this quark-antiquark pair. And the result of that is quite surprising, which is that the QCD vacuum actually fills itself with quark-antiquark pairs. You know, creates them for a little while, says, I like having these guys around, I gain energy, and therefore space-time, you know, and this is quite remarkable if you think about the vacuum. You used to think vacuum was empty space, which had some things sort of flitting in and out from quantum theory. But now the vacuum is just completely chock full of quark-antiquark pairs. And the characteristic scale of this interaction is hundreds of MeV, and so the energy density of these quarks in just empty space is about 100 MeV to the 4th, which is basically equivalent to the energy density in a nucleus. Okay, so the whole of empty space is really full of nuclear matter, and you think, shouldn't we know about that? Well, the answer is that we do know about that, and we know about it because of the proton mass. If you try and take a proton of these 3 quarks and you try and drag it through the vacuum, which is full of these quark-antiquark pairs, there's a continual interaction in which these things are jostling with these or annihilating against them and liberating one of the other quarks in that pair. And it's that interaction energy that is actually responsible for the proton and neutron mass, and therefore responsible for the fact that you're sat in this room and not streaming through space at the speed of light. Now, all of this we know is true in QCD only because we have a reenaction, but you know, we actually have QCD in front of us. We can observe it, we can see how it behaves. Actually, though, QCD is a hugely difficult mathematical problem. You see, mathematicians and physicists aren't actually that good at maths, in my view. We're rather good at things, particles that don't interact at all. And then what we do is something called perturbation theory, where we say, let's imagine there's some small interaction which makes a particle deviate a little bit. That we can do. But when you get a really tough problem like this, where there's a strong interaction continually trying to bring these things together or force them apart, all of those techniques break down. You've got to write down a complete solution of the mathematical theory, and we just don't have a clue how to begin on that. Well, so that's the sort of thing that people here at the Newton Institute have been thinking about and have been thinking about over the last few months. And I want to make a connection that has been made in the last 10 years or so for you between QCD and string theory. Actually, the original connection was made way back 30 years ago. And basically, it's that a quark and an antiquark are tied together by this sort of interaction energy of the QCD gluon exchange. And that looks somewhat like a piece of string, right? Or a rubber band. The more you pull it apart, the more energy it costs you. And indeed, you find that if you model very high spin mesons made of a quark and an antiquark, for example, you get some of the properties right by thinking of them as a piece of string. So the natural thing to do was to say, okay, let's see if we can replace this whole structure of QCD with a much simpler theory, say, in which we just have relativistic pieces of string. So what are those? Well, they're things that have some length, and they also have some tension, and those are the properties you know. Well, you don't even know the length, right, because they want to come back to zero length. But you can stretch these things, and then you know the energy that they have given a particular stretching. So, you know, this seemed like a sensible thing to do, but then a number of things started to go wrong. One of them that is a little hard to explain without going into the maths is that they like to live in 10 dimensions. Basically, nothing you calculate makes any sense unless they live in 10 space dimensions rather than the 3 + 1 that we live in. But something else that happens is that they turn out to have gravity in their theory. And you can sort of see that quite easily. There are a couple of sorts of pieces of string one can imagine in this sort of theory. There are ones whose ends are just kind of flapping around. And then you can have wave fluctuations on those, like this. And you can see that you can oscillate up and down, or you could oscillate in and out of the page. Now, if you step back from those pieces of string so that you stop being able to see their length, all you sort of know is that there's a fluctuation up and down and a fluctuation backwards and forwards. And those fluctuations look exactly like the polarizations of a photon. So, is it a bit dark? Apologies. So these sorts of strings naturally describe photons, gluons, and so on, the things that we have in our gauge theories. Now, in addition, though, you can imagine bits of string where you tie the ends together and you have little loops. Now, if you study this sort of setup, and it's even true of just a rubber band, there are two sets of waves in the solutions for wave equations on these strings, basically left movers and right movers, things going clockwise and things going anti-clockwise, and they sort of superposition when they're on top of each other, but they just move through each other and keep going. They're separate sectors. So these sorts of strings naturally have a guy that oscillates up and down and backwards and forwards, but they naturally have two of them because there are the waves going both ways around the string. And so these things naturally look like something that is something with sort of double the polarizations of a photon. And in fact, that is what the graviton of general relativity looks like. So for those who know, it's associated with a metric g mu nu. Mu nu, it has two vector-like indices. Its polarizations are like the superposition of two photon polarizations. So this sort of theory miraculously contains both gauge theories and gravity. And we know that our world contains both gauge theories and gravity. And in fact, quantum gravity is something that we've struggled for a long time to understand. So there was a lot of excitement about these theories. Drop this. QCD doesn't know anything about gravity, you would think, so this must have been rubbish, but maybe now we've got an ultimate theory of everything. The problem is that when you try and test gravity, it's very hard. It's a remarkable fact that if you take two objects and you try and measure their gravitational attraction, nobody has ever managed to do that on scales, distance scales of less than about a millimeter. Right? You know, we can probe these things down to atomic scales, nuclear scales, 10 to the minus 15 meters or smaller. But then we just drop gravity. It's so weak that we don't ever see it, and we only know about gravity on very long length scales. The result of that is that when we try and look for how gravity interacts with the quantum world, we just have no data. So there are theories, or they live in 10 dimensions, although maybe you can do something about that. That might be the theory of everything, but we have no data to test them with. So you know, there's still a hope here, but we're not finished on the theory of nature. I want to take you though in a different direction due to this gentleman Juan Maldaceno, who actually went back to this old idea and said, take this whole page and don't be put off by the fact that all of this doesn't look like QCD. Actually, it really is QCD, and it's just a very peculiar description of it. So we have in fact realized that the QCD string, that connection between two quarks, is a very peculiar object when thought of as a string theory that actually lives in a higher number of dimensions. So my sort of picture here is here are the quarks living on this 3 + 1 dimensional space like we do, but then mysteriously there are these extra dimensions that open up where these strings can propagate. And basically taking that seriously has led us to an entirely new way of calculating in QCD. This theory, in terms of the quarks and gluons, is a tough mathematical problem. We don't know how to solve it. If you believe, though, that these strings, and I should say it is only a conjecture, although it's quite a well-tested one, these strings living in some curved space-time are an equivalent description, then you suddenly find you've got an entirely new way of calculating in QCD. You just calculate classical general relativity, you look at gravity waves, and so on, and those are relatively straightforward to solve, and what you find is the answer to some problem that you just didn't know how to solve at all involving quarks. Let me give you an example of something you can do that I've been involved with. You can sort of chop this picture in half. So now this piece of string has a quark label up here, so it's an up or a down quark. And then in the middle here it has a color label, red or green, which of course gets tied up by the strong forces. You can look at those bits of string and you can say what happens in these strange curved spacetimes that are to do with QCD. And what you find is that those strings get stretched. They're not allowed to go down to zero length. And so then sort of length times tension is some energy. These quarks naturally have, in this theory, some energy associated with them, some mass. And that is the sort of stringy gravity version of what I was talking about before, about how the theory of QCD generates a quark mass out of nothing from these pairs of quarks that are created in space. On the next page I'll talk about another example that we've heard a lot about at this workshop. But I've got to sort of stick this in as well, which of course this is causing all sorts of confusions. We've discovered that this theory of quantum gravity, or this theory of gravity anyway, in this higher dimensional space, has this alternative description in terms of a lower dimensional gauge theory. Well, we live in a world with gravity. Could that mean that the real world should be described by some lower dimensional theory? It's possible, but so far no one's managed to really pin that idea down, but it's a fascinating one. Okay, so here's something that we heard at a workshop about a month ago, presented by Larry Yaffe, which is a beautiful example of using this duality. So he was interested in taking a heavy quark and dragging it through a cloud of light quarks and gluons. That's an impossible task to do that calculation just using QCD, but now on the other side of this duality, you can do that by talking about a long string, that's the heavy quark, moving through the gravitational background, which is supposed to correspond to the gauge fields. And he's got some beautiful pictures. So here's an example. The quark is about here, and it's being driven at subsonic speeds through the background here. And you can see it sort of pushes energy out ahead of it and leaves a hole behind it, which is the sort of thing that you might expect if it was a boat. And then you can also push that thing so it's suddenly going supersonic, and then you get shock waves coming out from where the quark is. So these are calculations you never imagined that you could do, but now you do at least have some handle using these string theory techniques. Okay, so I've gone off into the land of theory. Sorry, I'm a theorist. I was supposed to be telling you about the LHC, but this calculation is actually directly relevant to what is going to be going on at the Large Hadron Collider. So that one of those extra experiments I didn't talk about, extra detectors, was called ALICE, and this is going to be interested not in proton-proton collisions, but in heavy ion collisions. So in particular, they're going to take the nuclei of lead and nuclei of some more lead and smash them together and see what you get. So I'm not sure if you can see this, but this is a simulated event in which they have about 3,000 particles they're expecting to come out of this collision, and a total number of hits in the detector of about 700,000. So this is a massive technological challenge again to try and understand these collisions. But why would you want to do this? Well, it's a test of asymptotic freedom. If you take a large number of quarks and you stuff them into a very small volume, if you get those quarks close enough together, asymptotic freedom will set in and they'll stop interacting with each other. So that's what you would like to see, is if you crush nuclei together hard enough, what you'll get is just a gas of free quarks and gluons. Now actually, there have been some other experiments, particularly one at Brookhaven in the States called RIC, that have done similar things at lower energies recently. And what they suggest is that you can't quite get the quarks close enough in these collisions. Instead, what happens is that they sort of become this amorphous, very strongly interacting material. And so people talk about it being a strongly coupled liquid rather than a weakly coupled gas. So this is now an enormously complicated problem in QCD, again, because you've got to keep those strong interactions. The quarks aren't close enough together for it just to be a weakly coupled system. So now, this gauge gravity correspondence that I've been talking about is actually, turns out, it would seem, to be our best tool to describe what's going on in these collisions. And that's therefore very exciting. This means that at LHC we're going to be testing this very large construct of theoretical ideas that are all to do with the strong nuclear force, our understanding of the proton mass, and so on. Okay, I now want to sort of switch back to the proton-proton collisions to say what is it that we're hoping to find beyond our current understanding. So let's see what else there is that I've missed out from our description of nature so far. Everything in this room is made up of up-down quarks, electrons, and then there are these electron neutrinos that happen in the sun. But it's actually turned out, when we've done our collider experiments and used E equals mc squared to create more stuff, that we found an embarrassing rich of copies. So in particular, there are copies of the electron, one called the muon, which is heavier, and another one called the tau, which is heavier again, going up in sort of steps of roughly 100. They have their own neutrinos as friends, and there are also copies of the quarks. Charm and strange quark are the copies of the up and down in what we call the second generation. The top and bottom are the third generation versions of those. And for example, the top quark mass is 175 GeV, about 175 times the mass of a proton. These are really very peculiar things. They're identical in all respects to the electron up and down quark and so on, except that they're just more massive. The result of that is that they decay by the weak force into the things that we know and love and just become normal matter. But you can create these in experiments, and they would have been there in the early days in the Big Bang. So you immediately have a question of who needs these things, what are they for, and why do otherwise completely identical particles have different masses? And so that's one of the big questions that we have. The other thing that I should just talk about is the weak force. That again turns out to be a gauge theory. There are the equivalents of gluons or photons called the W and Z particles, which mediate these sorts of interactions. And they interchange up and down quarks or electrons and neutrinos in the same way that gluons interchange different colors of quarks. Why is the weak force so weak? Well, again, it's because of mass. These W bosons are very massive. It means that it's much harder to create them with the uncertainty principle because you need more energy, and therefore this interaction gets suppressed, which is why it is weak. But again, there's a question of why is it that these things have mass? In all our other gauge theories, we get things like the photon, which are massless. So that's the big question in our current understanding of particle physics, is what is the origin of mass? Well, we had an explanation of the proton mass, but unfortunately that's not going to work for the electron. The electron doesn't feel the strong nuclear force. That's why it doesn't get sucked into the nucleus of atoms. So there's no way that it knows about the universe being full of quark-antiquark pairs, so we need to explain where that electron mass comes from. But also we need to explain, for example, where the top quark mass comes from. It's much heavier than the up and down quark, even with this dynamically generated mass by QCD. We've got to explain that. And our best guess is something called the Higgs boson, and it relies on the sort of intuition that we've just got from QCD. If we want to give these things energy everywhere in space, we need to fill space with something, so that everywhere these particles go, there's something they're interacting with that gives them the energy that becomes their mass. And so we just posit the existence of such a thing, and we call it the Higgs particle, and we're going to fill space with these things. And then the electron will get its mass by bumping into these things in the vacuum. You may ask me, why is the vacuum full of these particles? And if I take at least the simplest model, I have no answer for you at all. We just know there has to be something there, so we put it in by hand. Okay? So you want to find this thing in order to start answering these sorts of questions. Well, how much of it must there be there? Well, if you want to explain these sorts of numbers, which are 100 times the proton mass, you've got to make this stuff about 100 times denser than nuclear matter, filling empty space. Of course, you don't want to give the photon the photon a mass, so the photon had better not interact with this stuff, so it had better be electrically neutral. Also, you don't want masses to depend on which direction a particle is going in, and that's what tells you that this particle is a scalar. In other words, it has no spin. If it had spin, it would pick out a direction about which it was spinning, and that would show up in the masses. But we don't see that, so we know that this must be a scalar. And in fact, this would be a new sort of matter that we haven't seen before. We've never observed a fundamental scalar in physics. But of course, there's other things. You may ask me, well, why does this stuff couple differently to the electron and the muon? And again, in the basic theory, we have no answer to that. We just say it does. We put in a number, which is the way that these things couple, and it doesn't really, therefore, explain it. It explains the origin of the mass, but not why they are the sizes that they should have. So what we really want to do is to get our hands on one of these things so we can start asking it those questions. And this is the big thing that the LHC is out to find. So how are we going to produce these Higgses? Well, they couple to things on the basis of their mass. So the obvious thing to do is to try and make them from heavy things like top quarks or W and Z particles. And these are 4 examples of processes where you, for example, fuse 2 gluons together through a top quark loop to make a Higgs particle, or use, and it's called Bremsstrahlung, off a W or Z particle produced by the quarks. So this is the hope, is that we're going to see these processes. Of course, this is actually only half of what you're looking at, because these things now all have to decay. You're smashing protons together, so if they decay into quarks, you're in trouble. You're just not going to see that. You know, of those 600 million events per second that you were throwing most of the ones you were throwing away were the ones which were just lots of quarks come out. So you want to look for things where these Higgses decay into something that is characteristically different, And an example is that you can sort of reverse this process. The Higgs can form again a top quark loop. And then rather than producing gluons here, though, it could produce 2 photons. So you can look in the data for the sudden appearance of 2 photons, and you reconstruct their energy back, and you find that every time you see them, you get exactly the mass of some new particle as the answer. And this is an example of how you look for a Higgs boson in these experiments. So we're hoping to find that. Of course, theorists are smart. We don't just have one model of the Higgs boson. There are many variants. Let me just tell you a couple of the sorts of ideas that are out there. One is that you might not like the idea of a new sort of matter, this spinning stuff, this scalar particles that we've never seen before. And a natural thing to do, therefore, is just to follow from QCD and make a Higgs out of, basically something with spin and something with the opposite spin, so that when they're bound together, it doesn't appear to have any spin. That would mean that there are new quark-like particles out there to be found, bound together by some new massively strong force, and that's one possibility for what might be happening. Another way to go is to say, okay, if we're going to find a scalar, this must actually be something that is now a new understanding of nature. We should embrace scalars. And there's a wonderful symmetry called supersymmetry, in which for every spinning particle, there is an unspinning partner that is the same in all respects except for that spin difference. That's a symmetry we haven't seen in nature yet, but it could be that the first discovery of a spinless particle is telling us that this is just out there, and we'll find this soon. So, we want to get our hands on this thing so we can find out just exactly what it's all about. All right, Nick, so that's a great little theoretical construct, but what if you do your experiment and you don't see a Higgs? The LHC is a fantastic experiment because it's basically a no-lose experiment. We know we have to find something. And in particular, what you can do in these experiments is to collide 2 W bosons. And if you have a theory without the Higgs in, and you do that collision and you do the calculation, we get the answer that the probability of an interaction is greater than 1. Well, nothing can happen with probability greater than 1. That makes no sense. In other words, we know our theory is sick at the sorts of energies that for the first time the LHC will be able to probe. So even if we're completely wrong about what's going on in this blob, there must be something there, and we should be able to see at least hints of what that is. Again, people have been inventive. We have some guesses for what this might be if it turned out to not be a Higgs. People have managed to construct theories in more space-time dimensions or with extra W bosons, and so the effects of all of those things show up in here that mean that there can be answers to this question that don't involve a Higgs. So there's something new out there to be found anyway. And in a sense, I'd say, this is the most exciting option. Yeah, we know about supersymmetry and QCD and all of these sorts of things. Wouldn't it be great if everything changed and we found something new? Okay, I will come to a halt at this point. The really exciting thing is that this stuff is all going to happen in the next couple of years, and I expect you'll find that the newspapers are just full of what's coming out of this. It's really just an amazing technological endeavour, never mind all of the physics that goes inside it. We'll be really penetrating what nature is made of. It's going to test our understanding of these ideas about the generation of mass in QCD. We've kind of staked ourselves on the existence of this Higgs boson. We think it's out there, and if it is, we're going to find it, basically. And if not, well, we'll find something really exciting and new. And then just the gratuitous plug on the end. If you enjoyed this talk and can't quite face sitting down with a quantum field theory textbook, I wrote a crime thriller that's on my webpage, and you can read it for free. And there's an introduction to the LHC in there as well. Anyway, thank you for listening. And
thanks, Nick. Nick's publicist drove a very hard bargain when we were negotiating. We've got time for a couple of questions. Anybody has any? Yes.
I heard that in principle, as you mentioned at the end, it's possible to count the amount of extra dimensions. In what sense and with what accuracy?
What was the question?
So the question was, can you, if there are extra dimensions, can you count how many of them, and how would you do that? And my suspicion is that the answer to that is it depends on your theory. So no, I suspect you can't. You're probably talking about the idea of there just being flat extra dimensions, and well, so then there's a connection that if you want to try and use those extra dimensions to solve some problems with the Higgs theory that you don't like, so then there's some assumptions in there, and I think at that point I'm going to back out. I don't know if anyone in the audience actually knows what the constraints are. I can look that up for you if you want to ask me afterwards, but it's not a straightforward question, I don't think.
Does anybody have a question they can answer?
Do you expect to see a fourth generation of particles?
Well, because a priori there's no reason why you shouldn't, but there are actually two arguments against. The first is that in all of these generations we've seen so far, the neutrino is massless, basically. It has a very, very tiny mass. So it would be very peculiar to find a fourth generation where suddenly there was a heavy neutrino, which was much heavier than anything we'd seen before. However, you can imagine that that would happen. The other constraint is that you can do very precise tests of low energy physics. And in those, as I showed you, what you see is photons bouncing off this stuff that's made in the vacuum. If there was a fourth generation, there would be loops of it out there being created by the uncertainty principle, and a photon in any, going between you and me would occasionally bump into that. So by doing a very precise low energy measurement, you should be able to see whether it's there. There are very tight constraints on putting in a complete fourth generation. Which isn't to say there aren't tiny little holes in the space where if you make the masses just right, you can get cancellations and get away with it. But I think most people are not expecting to find a fourth generation.
Okay, time is moving against us, so can we thank Nick again for